My name is Arun Srinivasa and I'm a professor in the mechanical engineering at Texas A&M. Today we are going to talk about the first step in the analysis, in the structural analysis of a system, which is system isolation and idealization. Okay, so let's get started. So what will we learn in this session? Well, let's see. Item 1, we will learn what is a free body diagram and why do we need it. I mean, most people, you have some idea about it, but we are going to do a much more rigorous version because of the fact that free body diagrams are very important in engineering. Okay. The second thing is, when you draw a free body diagram, what should you keep and what should you discard? Okay. And the third thing is some do's and don'ts about free body diagrams. So not an exhaustive list, but some ideas. Okay. So let's get started. But before we do, we begin by looking at the 5 steps that are needed for structural analysis. The first item is isolate and idealize. Okay. The second one is from pictorial view to a vectorial version. So this requires math and physics. This requires a lot of judgment. This requires some knowledge of basic math and physics. Analyze an argument. This also requires judgment. This again requires combine and calculate. So this requires actually quite a bit of math. And then check and conclude. By conclude, I don't mean finish. I mean make decisions. Okay, so conclude means decide. Right? The entire aim of doing calculations in engineering is to make decisions. Okay, so that's how it works. So this is the 5 steps, and I want you to really memorize these 5 steps because this will provide the framework for you to deal with any structural analysis problem. Okay, so that's why I wanted to kind of mention this. Okay, very good. We are going to look at step 1 in this particular session. Okay, so what's a free body diagram? It's first and foremost, it's a simplified representation of the system. It's a system that has been separated and idealized so that only external effects are shown. Okay, so this simplification is very important. In engineering, it's also a crucial means of communication. Okay, and the difficulty with this seems pretty straightforward, but the difficulty with this, especially in engineering applications, excuse me, is when the body is constrained and or it's not in steady state, that is, it's accelerating, then these things get into difficulties. Before we go into the details, I want to quickly show you Bloom's taxonomy. You remember we talked about this in your first class. Today we are revisiting this Bloom's taxonomy to show you that to draw free body diagrams does not require any calculation but requires a lot of judgment. Okay, so the first step in your analysis is very high in Bloom's taxonomy, even though it appears to be very simple. Okay, and what happens is, because it's actually fairly difficult, we usually make mistakes when we do this. And the problem with free body diagrams is that if your FBD is wrong, you cannot recover. You are really dead. It will kill everything else. So that's why paying attention to and drawing free body diagrams is important. Very good. So let's start. Let's say you want to do something very simple. You want to design a skateboard. Okay. Just to get you going, I'm just looking at it. And if you look at a skateboard, it's got lots of things in it. So if you look at it, it's got lots of parts, surprisingly lots of parts. It's got bearings, it's got something called a truck, it's got wheels, it's got this thing called a riser, deck, grip, tape, all kinds of stuff. So if you want to look at what are the issues when you're going to design, at least at a simplified level. So for a skateboard, at a designer level, you want to have something that's an exciting skateboard design. It looks cool, it looks exciting, so that's item number 1. And it has to have good smooth performance. smooth motion. Okay, but that's not all. There is a public safety issue, which is we have to ensure that the skateboard does not break during stunts, during use. So what happens is, in order to satisfy this thing, we have to look at this. That is, we need to find out what are the forces on the skateboard and check against the braking load. How much is the force and what's the braking load? We have to check that and figure out whether it is safe or not. Okay, so this is our task. This is why we need to do free body diagrams. All the structural analysis comes here. So how do we do this? Okay, we're going to draw a proper engineering free body diagram. What I want you to do is, before we proceed, get a paper, pen, so on, because I want you to see how to draw it and I want you to try your hand at it. So our idea is to draw a free body diagram of the skateboard. So the big idea behind this is we are going to shrink wrap the system with an opaque wrapper, as if you are giving somebody a present. So what it is that, imagine that you're going to hand the skateboard to somebody as a present. So what would you do? You take the skateboard and wrap it up. Right? That's the idea behind drawing a free body diagram. We are going to look at that, and in 2 dimensions we are going to replace the free body diagram with a chalk outline, like, you know, you have seen those kinds of things now, like this. So we only care about the outline. Okay, so that's step number 1. What the outline does is it divides the world into inside this region and outside. That's the purpose. So we are going to draw something which will separate this thing into inside and outside. This is the isolation step. That's why it's called isolate. Then we come to the idealized part, which is we ignore everything that's inside. I don't really care. The skateboard looks like this, whatever, and there are lots of parts inside. I don't even care about them. So everything that's inside our outline, we don't care about. That's nice, no? Now, the next thing is we're going to replace everything outside the skateboard with either force or moment. Forces or moments. Or moments or torques. That's it. So the entire external world is represented by forces or torques. And this representation of the external world with forces and torques is the hard part about a free body diagram. Okay, so let's get to that. The idea is a free body diagram. A free body diagram is something where only the external forces, effect of the external world on your system, is shown. So that means here is the side view of the free body of this skateboard. I don't care what's happening to the bearing, nothing. All of this is completely solid. So external world, what is it doing? Hey, there are people there, but they're not affecting it, so nothing, no force. But the ground is pushing, so we will draw something like that. This is ground. Notice first that the free body is floating freely, and the ground is replaced with forces, and the feet are replaced with forces. We will talk about this in a little while, but basically the idea is everything is just force and torque. That's it. Okay, if you do this right, we have to decide how the external world acts on the system. So it has to pull, push, drag, twist or bend the system. So what are the 5 things? Pull, push, drag, twist and bend. So pull, the technical name for pull is tension. The technical name for push is compression. The technical name for drag is shear. The technical name for twist is torsion. And and the technical name for bend is bending. So that's the one thing that's the same, but notice the other ones. Tension means something is pulling on the object. Compression means something is pushing on the object. Drag, shear means something is dragging the object. Twist, torsion means something is twisting the object, and bend is something is bending the object. See what I mean? So these are the 5 things. Okay, so if we know how to convert the external world into one of these things or combinations of these things, you are done. Okay, so we draw these effects by drawing arrows. I showed you some arrows. We will get into more detail. I'm just giving you the big picture here. Okay, and we do not include what the system is doing to the surroundings. So to give you an idea, let's say you're walking down a dark alley and suddenly a bunch of people are attack you. What you care about is what their fist is doing to your face, right? You don't care about what your face is doing to their fist. So in the same way, when you draw a free body diagram, you have to see what the external world is doing to the body, not what the body is doing to the external world. We don't care about what the body is doing. We only care about what the external world is doing to the body. Okay, that's how it works. Okay, we don't care about how the body is moving. We'll let Newton tell us what's going to happen with that. We just draw the external world. That's it. Okay. Given this idea, let's draw the free body diagram. So I am first going to draw the skateboard side view there, and everything is blacked out. So I don't know what is inside. I don't care what is inside. So first point is free floating. It has to be free floating. Don't draw it directly there. That's very bad habit. Please make a separate picture. Okay, that's item 1. Item 2, now let's see. I have removed the ground, right? What's the ground doing to this body? Well, it's pushing up. Right? And I don't know by how much. We don't worry about it right now. We just say, okay, the ground is pushing up. That's ground. What else is happening to it? Well, the skater's feet are pushing down. What else is happening? There is gravity acting on this. So center of earth is pulling. And the magnitude of this is known. M skateboard times G. That's my free body diagram. No, it's not over because the skater's feet are also dragging on that. We don't know which way. F skater drag. F skater drag. This is the full free body diagram. It's kind of messy. Later we will clean it up, but I just want to show you all the forces. This is skater push down. So this is compression from the skater. This is shear from the skater. This is compression from the wheels, that is from the ground. I'm sorry, not from the wheels, from the ground. And this is the tension from the center of the earth, gravity. Now, if you drew it, you're probably wondering what happened to the weight of the skater. So we will talk about that next. Why did we not put the weight of the person standing on the skateboard? The reason is that the skateboard knows only that there is something pressing on it. So the skateboard is aware only, feels only the skater's foot. The earth, gravity acts on the person, not on the skateboard. So if you draw the person, then you will have F skateboard, and here is gravity, mg, and then the skater will have equal and opposite forces there. The skateboard will have these forces. You see what I mean? But the force of gravity is acting on the skater, not on the skateboard. The skateboard gravity is just mass of the skateboard times gravity. So please remember that. So don't move forces around. This is a very important point. We'll talk about that a little bit. So the force of gravity on the skater shows on the skateboard through the feet. So what the skater is doing is transmitting the force of gravity to the skateboard through the feet. This is actually kind of a hard thing to get. You have to be very literal. You have to say, okay, look, there's only the skateboard, the skater's feet touching the skateboard, right? So that's a very important idea. So please remember that anything that does not cross the shrink wrap boundary is ignored. So if you look at our skateboard free body diagram, anything that does not cross this boundary is ignored. So only these things are there. The skater's force is not crossing this boundary. So we ignore this. Right? That's item 1. And there are only two kinds of forces. What do I mean by two kinds of forces? First, push, pull, drag. Right? These things, which are called contact forces. The other one, if it is not contact force, the only other forces that are there are gravity, magnetism, and electrostatics. And in our case, we don't even care about magnetism and electrostatics. We are only worried about gravity. So other than gravity, everything else has to be contact force. This is hard for you to actually use because in your previous classes, you may have all kinds of other things that have been included. So you have to be very careful about doing this. Every force has to pass a particular test. Force at a point P has to be because some external object, which you should be able to name, is pushing, pulling, dragging the system here. So if you look at our skateboard, if you ask, what is this force? So the answer is, this force is here because the ground is pushing the system here. If you cannot write this statement, then you should ask yourself, is there really a force? Okay, that's how it works, and that's the basic idea of drawing a free body diagram. So remember that we ignore everything that is inside the body, and we replace everything that's outside the body with either a force or a combination of forces or a torque or a combination of torques. That's all. Okay. Applying this in a systematic way takes some judgment because you have to know how to replace the external world with corresponding forces and torques. That is the high level judgment that you have to do, and that's the hard part. Okay, thank you very much.